Hi, Chapter 2 focuses on basic chemistry. If you've had chemistry before, this should all be reviewed. If you have never had chemistry, then you have a little bit of catching up to do. So we'll do chemistry that's appropriate for biologists. It's some basic chemistry, and it may emphasize different things than a chemistry course emphasizes. So we'll start with 3 pretest questions. The first question is, the 4 elements that constitute 96% of human body mass, including water, are abbreviated as follows. Okay, so there are sort of 2 parts for this question. You have to know what the chemical abbreviations are for the most common elements and which are the 4 most common elements. And the correct answer is D. Carbon, hydrogen, oxygen, and nitrogen. Number 2, true or false. Students love true or false questions because you can guess it and get it right half the time. When elements combine to form a compound, the physical and chemical properties of the compound are the same as the original elements. Example, Na plus Cl is NaCl. Okay, that's a false statement. We'll learn later about properties of sodium and chlorine and how different they are than the properties of sodium chloride. Sodium chloride is table salt. Number 3. The atomic number for Na, sodium, is 11. The mass number of Na is 23. Sodium has how many protons and how many neutrons? This one's a little harder. Okay, so the atomic number is the number of protons, which is 11. So sodium has 11 protons, and the mass number is 23. The mass is the number of protons plus the number of neutrons. So it has 11 protons, 11 plus 12 is 23. So 11 protons and 12 neutrons. So the correct answer is C. Okay. If you got those all right, then you've had chemistry and you kind of remember some stuff. If you didn't get them right, we'll catch up. So life is composed of matter. Now, not everything is matter. There are things in the world like light, which is electromagnetic radiation, which is not matter. But matter is anything that occupies space and has mass. So mass is something we can think of as being similar to weight. It's not quite the same since you'd weigh differently on the moon than on Earth, but anything that has a weight to it and occupies space is matter, and life is made of matter. Okay, there are 92 basic substances that matter is composed of. We call those substances elements. And elements cannot be broken down into simpler substances. We give every element a 1-letter abbreviation or a 2-letter abbreviation. So for example, sulfur is one of the 92 elements, abbreviated S. Calcium is one of the 92 elements, abbreviated Ca. We don't have to know all 92 elements. It turns out there are a subset of elements that make up most of what living organisms are composed of, and 96% of living organisms come from just 4 elements, from carbon, oxygen, hydrogen, and nitrogen. So let's compare the elements that are found on Earth to the elements that are found in living things. So humans, for example, are 65% oxygen, 18% carbon, 10% hydrogen, 3% nitrogen. So those are the big 4 that together make up 96% of living matter. In the atmosphere, in the air we're breathing, it's 21% oxygen. There's hardly any carbon, there's hardly any hydrogen, and it's 78% nitrogen. So the air is very different than a living cell. Similarly, within the Earth's crust, within the Earth itself, it's 46% oxygen, hardly any carbon, hardly any hydrogen, hardly any nitrogen. Okay, so living things are enriched in certain things, especially carbon relative to the atmosphere and Earth's crust, especially hydrogen relative to atmosphere and the Earth's crust. The smallest particle of an element, if you broke an element down and you had one particle of it, you'd have an atom. Okay. Atom and the three subatomic particles that make it up are the smallest particles of matter that biologists care about. If you talk to a physicist, they'll talk about quarks and muons and antiquarks. All those things are irrelevant to biologists. But you will have to understand an atom and the three subatomic particles that make it up, the proton, neutron, and the electron. The atomic nucleus is the center of the atom. It contains the protons and the neutrons. And around that atomic nucleus are electrons orbiting or circling around the nucleus. So protons, neutrons, and electrons are the three subatomic particles that make up atoms. You'll have to know the key properties of these subatomic particles. So the charges of a proton are +1, of a neutron is 0, that's why it's neutral, of an electron is -1. The mass of a proton is 1, the mass of a neutron is 1, the mass of an electron is close to 0. It's actually 1/2000. So it would be like saying, let's measure the weight of a cannonball, and then suddenly a fly lands on it. Well, would you have to remeasure it? No. Next to the weight of the cannonball, the fly is insignificant. So we'll just call an electron 0, although an electron is matter and does have weight. So this figure is showing you that the protons and the neutrons are in the middle in the atomic nucleus, and the electrons are circling around in orbital shells. Atoms each have a standard number of protons, and we'll start out assuming that the atoms are neutral, so they'll have the same number of electrons. When we ask what atom you have, we say how many protons does it have, or what's the atomic number. If you have a certain atomic number, it always tells you what the element is. Every element has a distinct atomic number. If you have 6 protons, you always have carbon. If you have 1 proton, you always have hydrogen. Okay? Atomic mass is the number of protons plus the number of neutrons. Sometimes you can have different numbers of neutrons. So people know about carbon-12. Carbon-12 has 6 protons and 6 neutrons, but there's also carbon-14. Carbon-14 has 6 protons and 8 neutrons. 6 protons makes it carbon, and the number of neutrons can vary. Well, so here's another kind of carbon, carbon-13. Carbon-13 would have 6 protons and 7 neutrons. Most carbon is carbon-12. Okay, if you have different numbers of neutrons, you have isotopes. Most hydrogen has no neutrons. It's the only element that has no neutrons, but some hydrogen will have 1 neutron, and sometimes you get hydrogen with 2 neutrons. You can click on this and see a simulation. You'll probably have to go to the downloaded PowerPoints. So radioisotopes are a common research tool. So this is showing that they unearthed some sort of little dinosaur. And sometimes you have bones. They would never destroy a piece of the main dinosaur, but there might be something nearby that they could get a radioactive date on. And if you get a radioactive date of something else that's in this sediment, let's see, you probably would not use, you wouldn't use carbon to date dinosaurs, because carbon only goes back as much as about 30,000 years. So carbon's good for dating parchment paper from the Egyptians that was 5,000 years old, and things that are very recent, back to about 30,000 years old. Okay, they say 50,000 years for carbon dating. Okay, but other isotopes could be used to date this rock that the dinosaur was caught in, and by dating the age of the rock, when the rock formed in the sediments, capturing the dinosaur, that would give you an idea of how old the dinosaur was. This is the periodic table of the elements, and you can see the elements going left to right are arranged in rows, and the rows are arranged in the number of protons. So hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, beryllium has 4 protons, and so on. If you go down, they're arranged going up and down by the number of electrons in the valence shell, in the outer orbital shell. We'll come back to that. Okay. Even though there are 92 naturally occurring elements, the living cells only have a subset of those elements, and we'll look at them in a minute. Okay, so besides the atomic number, traditionally they give you the symbol for that element, and they give you a weight. And the weight is an average of the different isotopes out there. So most hydrogen, and we'll assume hydrogen, has 1 proton and no neutrons and 1 electron. Okay, but occasionally you get isotopes with more than 1 neutron. So all this to the right is giving you the average weight of a hydrogen atom. You really don't have to worry about that. Okay, so assume to start that atoms have a neutral charge. So here's hydrogen with 1 proton and 1 electron. In the Bohr model, they just draw a circle to show the orbital shell. The farther you are away from the proton, the more energy in the orbital shell. Chemists don't like this. They say they don't really circle around in a circle, but it's a simplification for biologists. You only have to know about the first 3 orbital shells. Chemists will teach you about more. Okay, so the first orbital shell is filled with 2 electrons. So it's like an apartment that will only hold 2 people, then it's full. So what happens if somebody else wants to rent the building? They have to go up to the next floor. The second orbital shell is filled with 8 electrons. So you see here, there are 8 electrons. And for our purposes, we'll say the third orbital shell is filled with 8 electrons as well, although a chemist will tell you something a little bit different. So somewhere along the way, you should memorize the first 3 orbital shells are filled with 2, 8, and 8. Okay? If the orbital shell is full, if the outer orbital shell is full, it's called the valence shell. The outer orbital shell is called the valence shell. When the outer orbital shell is full, the element is non-reactive. So helium is non-reactive because the first orbital shell is full. Neon is non-reactive because its outer orbital shell is full. And argon is non-reactive because its outer orbital shell is full. Okay, so everything going up and down has the same number of, same amount of reactivity, because in this case, the outer orbital shells are full. Conversely, if we look at group 1, Group 1 elements are very reactive. Okay, there's one electron, and it needs 2 electrons to be full, so hydrogen is very reactive. Lithium has 1 electron. You need 8 to be full in the outer shell. It's very reactive. And sodium, there's 1 electron in the outer shell and needs 8 to be full. It's very reactive. All right, so the answer to this one is on the last slide. Going up and down the column with helium, neon, argon. They're sometimes called the noble gases, and Nobel was a guy who the Nobel Prize is named after, Nobel. It's somebody's name, not the word noble. Not like saying the king is very noble. Okay, so the number of electrons in the valence shell determine how atoms interact. So chemical reactions are changes in distribution of electrons between atoms. And atoms are stable in the valence shell when the outer electron orbital shell is full. When that's not full, atoms are reactive. All right, chemical reactions. So if you don't have a full valence shell, electrons are passed to form new substances. Reactants are the starting substances, the substances that react. Products are the substances that are formed. In this case, water and oxygen. This reactant is hydrogen peroxide, H2O2, and when it reacts, it releases oxygen gas, and water is formed as well. If you look, you'll see that there's the same amount of hydrogen on the left and right. 2 times 2 is 4, 2 times 2 is 4. The same number of oxygen atoms on the left and right. 2 times 2 is 4, 2 times 1 is 2, plus 1 times 2 is 2. So 2 plus 2 is 4. If there is no subscript, it means there's one of them. Okay, that was called conservation of matter, that we had the same number of atoms on both sides. Right. Molecule. When you have 2 or more atoms joined by covalent bonds where they're sharing electrons, that's called a molecule. A covalent bond, what are you sharing? You're sharing electrons in the valence shell in an aqueous solution, and most biological reactions are going to occur in an aqueous solution. The covalent bonds are the strongest kind of bonds. All right, so a covalent bond forms when 2 atoms react by sharing electrons. So hydrogen needs 2 electrons to have a full valence shell. Oxygen needs 8 electrons in the outer orbital shell to have a full valence shell. So 2 hydrogens will bond to the oxygen by covalent bonds. Now this electron pair is shared. So hydrogen has 2 electrons in its valence shell. Hydrogen has 2 electrons in its valence shell. And now oxygen has 8 electrons in its valence shell. So water is non-reactive. Sometimes you can form a double covalent bond. Molecular oxygen has 2 oxygen atoms forming a covalent bond. It's actually a double covalent bond because 2 electron pairs are shared. You can watch this video from Ricochet Science on how covalent bonds form and a second kind of bond called an ionic bond, which we'll look at in a second. Okay, so that's a nice video, not very long. You may have to download the PowerPoint for the link to work. I'm not sure if it will work from the YouTube video. Okay, so in ionic bonds, atoms complete their outer shell by gaining or losing electrons. And this leaves the atom with an imbalance between protons and electrons, resulting in ions. Ions are atoms that are short an electron or have extra electrons relative to the number of protons. And the charges are what are holding it together, and it's called an ionic bond. So here's an example. sodium gives up its electron to chlorine. Now sodium has one less electron than proton, so it's positively charged. Conversely, chlorine has an extra electron relative to the number of protons. It's negatively charged, and these charges hold it together. This is an ionic bond in an aqueous solution. In water, ionic bonds are weaker than covalent bonds and will come apart just due to physical attractions between sodium chloride and water. And we'll see that at the end of the chapter. So if you want to know, do molecules or ionic compounds have the same chemical and physical properties as the elements that make them up? Let's look at the next 4 slides and see if we can answer the question. Here is sodium. Sodium is a metallic substance. It's a soft metal that a chemist can get a hold of, but you or I can't. And see what happens when you toss a piece of sodium into a pond. So go ahead and click on that and see what happens. Chlorine. Chlorine can be a liquid, and some of it evaporates into a gas. People use chlorine in their pool to kill bacteria. People use chlorine and Clorox bleach to make things white. So it's a very reactive molecule, and it can be poisonous. So what happens when you combine sodium, which is very reactive, and chlorine, which is very poisonous? You get table salt, which is non-reactive and edible. So you can't always predict what the properties of substances are going to be when you make new substances from old substances. People who are chemists spend their time building new things, and sometimes they have very good predictive power on what the new things will do, and sometimes they build the new compounds and they say, wow, I didn't know it would be like this, and they discover things about that. Okay, so table salt is held together by the charges between the sodium and the chloride ions. It's not held together by covalent bonds, but by ionic bonds. So you have an ionic compound, not a molecule. And the new substance has different chemical and physical properties from the atoms that make it up. All right, go ahead and look at these 4 substances, O, O2, H2O, and CH4. Tell me, is it the smallest part of that element, or is it made of more than one atoms bonded by covalent bonds? Then go look over here and tell me, is it an element or a compound? An element is made of only one kind of atom, whether it's a single atom or a molecule. A compound is always a molecule, but it's a molecule made of 2 different kinds of atoms, or 2 or more kinds of atoms. All right, you think you have this down? So O stands for oxygen, and you have 1 particle of it here. So here O is an atom. O2 means 2 oxygen atoms are joined by covalent bonds. So here you have a molecule, H2O, 2 hydrogen atoms and an oxygen atom joined by covalent bonds, a molecule. And methane is CH4, a carbon atom joined covalently to 4 hydrogens. So that's a molecule as well. Okay. O is an element. There's only 1 kind of atom. O2 is an element. There's only 1 kind of atom. It's an elemental substance. There's also O3, which is an elemental substance. That's ozone. H2O is a compound. It's made of 2 kinds of elements, hydrogen and oxygen. CH4 is a compound. It's made of two kinds of elements. You can have compounds like C6H12O6, which is glucose made of 3 kinds of elements, more complex compounds made of 4 kinds of atoms, and so on. I want to talk about polar covalent bonds in the water molecule. They come about because of unequal sharing of the electrons. So everybody knows that water is H2O, and it's formed by covalent bonds with the hydrogen. The electrons arrange themselves so they're as far apart from each other as they can, and it winds up that hydrogen is sticking out from the top at a bit of an angle. So when these covalent bonds form, oxygen is a very electronegative element. What does that mean? It means it has a larger pull on the electrons than hydrogen. So even though these two atoms are sharing an electron pair, the electron pair is often closer to the oxygen than the hydrogen, and the same with this pair. So the electrons spend more time orbiting the oxygen, or are closer to the oxygen than the hydrogen. As a result, there's a partial negative charge on the oxygen. There's a partial positive charge on both of the hydrogens. That's the Greek letter delta positive. So that is brought about from the unequal sharing of electrons, which we call a polar covalent bond. If you have an equal sharing of the electrons, it's a nonpolar covalent bond. And methane is a perfect example, CH4. In CH4, the carbon and hydrogen share the electrons equally. When they share the electrons equally, there's no charge separation, they're nonpolar. Carbon dioxide is another example. The carbon and the oxygen share the electrons equally. It's a nonpolar covalent bond. So let's focus on water now. Water is the most critical molecule for life on Earth. When they go to other planets, the first thing they look at to see if there's life is they say, is there water? We can't imagine water not being there and life being present. Water is very central to life. Okay. 2 things about water. It's a polar molecule. It has this charge imbalance in the covalent bonds. And as a result of these charge imbalances, it forms something called hydrogen bonds. So the partial positive on the hydrogen makes a little tiny pull on the partial negative on the oxygen on the next water molecule. So the covalent bonds, I promise I'll ask you this, the covalent bonds are within a water molecule between the hydrogen and oxygen. The polar nature of these bonds is creating the charge separation, and then these partial charges attract between different water molecules. A hydrogen bond can form between hydrogen, which is partially positive, and oxygen, which is partially negative. It also sometimes forms between hydrogen and nitrogen in other molecules. A hydrogen bond is about 5% as strong as a covalent bond in an aqueous solution. So it's a much weaker bond than a covalent bond, but it's still very important. So when water molecules are in a liquid state, these hydrogen bonds are forming them into a network of water molecules. It's a very sticky molecule. All right, so you should be able to go back and answer these questions. What are the 4 major elements of living things? And if you remember, this was one of the questions on our pre-test. They're carbon, hydrogen, oxygen, and nitrogen. So living things, 96% of them is those 4 elements. Number 2, why is NaCl called an ionic compound and not a molecule? Because molecules are formed by what kind of bonds? Covalent bonds, and NaCl is held together by the charges of the ions. Na positive, Cl negative, that's what holds them together. Number 3, distinguish between ionic, covalent, and hydrogen bonds. Okay, so in an aqueous solution, not in air, but in a water solution, covalent are the strongest, and they're formed by electron sharing in the valence shell. Ionic are the next strongest in an aqueous solution, and they're formed by attraction between positive and negative charges when one atom donates electrons to another atom. And hydrogen bonds are the positive and negative attractions formed by a partial positive and partial negative charge. So you can see why they would be weaker than ionic bonds. Ionic bonds are held together by a full positive and a full negative charge. Number 4, is neon a reactive atom? Explain. So look at the periodic table, see whether the valence shell, the outer shell, is full, and you'll see that neon has 8 electrons in the valence shell. So you can throw some neon gas into a glass tube, and if the glass tube is different colors, you'll electrify the neon gas, and it won't react with the electricity, but instead it will glow a little bit, and that little glow will make the tube have different colors. So neon's non-reactive. It's an inert gas. What is the weight and charge of a proton, neutron, electron? Proton, +1, weight of 1. Neutron, charge of 0, weight of 1. Electron, charge of -1 and weight of 0. Is O2 an atom or molecule, element or compound? O2 is a molecule, and it's an elemental substance, so it's an element. Water is a really important substance for life, and it has a lot of unique properties. It's the only substance we're familiar with that at normal temperatures is found in 3 states of matter: liquid, gas, and solid. So solid, the solid form of water we call ice is pretty interesting. Because of hydrogen bonding, the atoms actually arrange themselves in a state further apart than in the liquid form. So the solid form is less dense than the liquid form, and that's why ice floats. Okay, that's important because in the wintertime, lakes freeze over on the top, and different sea life will live below those icy surface. So some people, if you live in Minnesota, maybe in the wintertime you go ice fishing, you drill a hole in the ice, and the fish down below will do just fine. And if you know what you're doing, you're lucky, maybe you'll catch some of those fish. All right, let's think about another substance we're familiar with to see if this is really a true statement. So here's wax. So they sell paraffin wax at hobby shops. You can make it into candles. And if you melt some wax and you take some solid paraffin wax and you throw it into some liquid paraffin wax, what do you think it will do? Will it be like water? Will it float in the liquid paraffin wax? Okay, go ahead and click on the YouTube video and see what you find. Okay, water has a high specific heat. What does that mean? It means it takes a lot of energy to heat up water. If you put in a cooking pan of metal and you're going to boil some water to make spaghetti, if you touch the pan in about 3 or 4 minutes, you'll burn yourself. But if you put in a bunch of water and put your hand in the water still hasn't heated up. Okay, why does it take so much longer for the water to heat up? Okay, it takes a lot longer because when we say something heats up, we mean the molecules are vibrating more quickly. In order for water molecules to vibrate quickly, you have to break hydrogen bonds. And to break those hydrogen bonds, it takes a lot of energy. So it takes a lot of energy to heat up water. Okay, it has a high specific heat. Okay, but conversely, once you've heated that water, your coffee or tea will take a long time to cool down. Why is that? Because when we say it's cooling down, we mean the molecules are vibrating more slowly. So they're vibrating more slowly, and as they vibrate more slowly, boop, a hydrogen bond forms. And when a hydrogen bond forms, it gives off a little bit of heat. So water tends to resist heating, but it also stays warm a long time. It tends to resist cooling. So it's a nice medium for living organisms to have inside of them because it tends to buffer temperature changes. And as we all know, humans want to keep a set temperature. All right, so that's the answer to what I just explained, so you can take and read that through on your own. Okay, another property of water. When water evaporates, it carries off heat with it. So when it goes from liquid to gas, it carries heat with it. It's called evaporative cooling. And so here in Phoenix, where we have a dry heat, it can be 90 degrees out, and if it's 10% humidity, you can be outside and not feel so hot because you're carrying heat off when the water evaporates. But if it's the monsoons or you're living in New Jersey, that same 90 degrees with 40 or 50% humidity, you're out there, you're dying because that heat's not being carried off your body. This slide explains why table salt dissolves in water. So here's an ionic compound, sodium chloride, and table salt, if you look at it under the microscope, it forms these very square structures. And if you looked closely, closer than you could really see with a microscope, maybe with a powerful electron microscope, you would see repeating units of chloride ions, Cl negative, and sodium ions, Na positive. Chloride ions, Na sodium ions, and just repeating pattern. Well, when you put it into the water, the negatively charged oxygen attracts the sodium, which is positively charged. So the oxygen surrounds the sodium and pulls out one sodium ion at a time. Conversely, the positively charged or partially positively charged hydrogens pull out the chloride ion one at a time. And so sodium ions and chloride ions are pulled apart from the sodium chloride, and that's what makes salt water taste salty. Okay, so you can fill in the blank, just what I explained. And they say this is a hydration shell. It's water forming around either the chloride ion or the sodium ion. An ion is when you have a charge on an atom that's either lost an electron or gained an electron. Hydrogen bonds also create cohesion among water molecules. So if you've ever been to a daycare and played how many drops of water can fit on a penny, then you know that you can form a dome on the top of a penny and the water sticking to one another through hydrogen bonds. That's called cohesion. So these cohesive bonds form this dome on the penny. Similarly, the penny itself is a charged molecule because the metal has charges on it, and the water sticks to the penny, and so that's called adhesion. So when water sticks to itself, it's cohesion. When it sticks to other molecules, that's adhesion. Surface tension is caused by the fact that water forms a little skin on the top. There's actually more hydrogen bonding on the top than lower down, and a chemist would probably say it's thermodynamically or energetically unfavorable for a water molecule to be sticking out above the surface. So you get more hydrogen bonding at the surface of the water. It's like a little pudding skin on the surface. And if you have something that's light enough and has great enough surface area, it can float on the surface, or an insect might be able to walk across the surface. This is a phenomenon called capillary action, and the adhesion between the sides of the tube will actually pull water up the tube. Here's some sort of water strider, and it has a light enough weight and enough surface area on its legs that it can actually walk across the little skin on top of the water without breaking through. What accounts for water's ability to dissolve different molecules, or its solvent properties? Well, a lot of ions have full charges, like sodium chloride, +1 and -1, and water is polar, it's partially charged. And so molecules that are fully charged or partially charged dissolve very well in water because water is attracted to them. Water is a solvent, it's the dissolving substance, and the things that dissolve in the water are called the solute. So when you have an aqueous or water solution, water is a solvent, and the solutes are charged or partially charged molecules that will dissolve very well in water. It's a solvent of life. Okay. If instead you add a nonpolar compound, like an oil droplet, the oil droplet won't dissolve in water. You can shake oil and water together to get a suspension. You'll have little droplets in your salad dressing. You'll quickly pour it on your salad, and then you'll set the salad dressing down, and it will separate out again because the water doesn't have anything to grab onto with these nonpolar oil droplets. So if you have a greasy bicycle chain and you want to clean it off because you've been riding in the desert, got a lot of dust on it, this looks like Sedona, are you better off spraying water on it? Or would you be better off cleaning the bicycle chain with WD-40, which is a petroleum-based solvent? Okay, so the answer is that grease is non-polar, it's uncharged, while water is polar, partially charged. So chemists will say that like dissolves like, that charged substances dissolve other charged substances. So water dissolves charged molecules very well, but not something nonpolar like grease. So something nonpolar would be dissolved better by a nonpolar solvent. So something like WD-40, if you spray it on a rag and then wipe it on the chain, it's going to dissolve the grease much better than water. Okay, pH. So we know that living things regulate temperature very well, but there are other things they regulate very well, like different kinds of dissolved substances, the amount of sodium, the amount of chloride, and something called pH. pH has to do with the H-positive concentration in solution. Water will naturally separate a very tiny bit into H-positive and OH negative. And certain substances will increase the H-positive in the solution. Okay, in terms of molarity, neutral water, pure water, will have 1 times 10 to the negative 7th moles per liter of H-positive and 1 times 10 to the negative 7 moles per liter of OH negative. It will be in balance between the two. Okay? OH is sometimes called the hydroxide ion, and H-positive is the hydrogen ion. Okay, if you have more H-positive than that, you're acidic. If you have less H-positive or more OH negative, then you're alkaline or basic. And life usually exists better where H-positive and OH negative are in balance or neutral. Instead of talking about saying you have 1 times 10 to the negative 7th H-positive, what we do is we take the negative logarithm of the H-positive concentration and we say the pH is 7. So as the H positive increases, the numbers go up by a factor of 10. So pH 6 will have 10 times more H positive than pH 7. pH 5 will have 100 times more H positive than pH 7. pH 4 will have 1,000 times more H positive. So pH 4 represents a molarity of 10 to the negative 4th. Okay, so you have to know that 0 to 6 are acids, 7 is neutral, 8 to 14 is basic. Okay, and it's very important. Our blood is about pH 7.4, and if it goes up or down 1 pH unit from that, then you die. So there are a lot of things that we're familiar with, like temperature, and we know that temperature exists in a narrow range, but there are other factors as well that are carefully regulated by living things. So here's a problem. I'll have a similar kind of problem on the test probably. The pH seawater is 8. The pH of black coffee is 5. Which is more acidic? So that's the easy part of the question. Above 7, you're a base, so that's a base. Below 7, you're an acid, so 5 is an acid. And then which has more hydrogen ions and how many times more? Okay, so the black coffee has more hydrogen ions. How many times more? 8 minus 5 is 3. 10 to the third is 10 times 10 times 10, or 1,000. So there are 1,000 times more H positive in black coffee than in seawater. So just like we can raise body temperature or lower body temperature, we have ways to maintain a neutral pH in our body. We have buffers or chemicals that will absorb H positive when there are too many of them. And we have chemicals that will make our cells more acidic, but we need more acidity. All right. So carbon is the backbone of life's molecules. It's sort of the central skeleton of organic molecules. That's why it's important for life. It's the best electron sharer in the world. It has 4 electrons as a valence shell, so it can form a wide arrangement of molecules. If you go on and study organic chemistry is the chemistry of carbon. If you ever use gasoline or plastics, that's hydrocarbon chemistry. That's the same idea. And hydrocarbons are made from dead living organisms, from oil, from fossil fuels. Okay? And we're going to look at functional groups. Groups are part of biological molecules that react. Okay, so this tells you what I just told you, that carbon is a very available molecule. It has 4 electrons in a valence shell, and these 4 electrons can form 4 covalent bonds. Here are hydrocarbons. Hydrocarbons are hydrogen and carbon linked together. So here's methane. So methane's natural gas. Sometimes on a dump, methane gets produced by all the garbage in the dump, and they burn it off. Or sometimes they'll actually pipe it and sell it to different facilities. So they'll collect it if they're very clever. Here's methane, the molecule we saw before. And you're seeing carbon in the middle. It has 4 electrons in the valence shell. So it will form 4 bonds. The simplest kind of carbon is if it forms bonds with hydrogen, it makes methane. Methane is natural gas. So think of the carbon to hydrogen bond as having a lot of energy. Functional groups. Functional groups are groups of atoms within a molecule that confer specific properties. Specifically, they're often involved in the chemical reaction of biological molecules. So from these particular functional groups, the ones you'll have to know, you'll see over and over again, are the hydroxyl group. So OH, oxygen and hydrogen, are very reactive, and it's called a hydroxyl group. Okay. Methyl group, we won't talk that much about methyl groups, but you'll probably learn about them later on. That's a CH3 group. Don't worry about carbonyl and carboxyl groups, but amino groups are part of amino acids. So that's a nitrogen. Remember, nitrogen is one of the big four, and NH2 is an amino group. When you see an R over here, they're just telling you it's an attached to another atom or molecule. So it doesn't, it's like putting an X in a mathematical equation. So don't worry about what the R is. They're just saying, oh, it's attached to something else. A phosphate group. A phosphate group is a phosphorus atom surrounded by oxygen. Here they're showing the oxygen with hydrogen. Usually the hydrogen are dissociated, and you see the oxygen with a negative charge when it's lost that proton. Sulfhydryl group, okay, so that's telling you it's a sulfur group bound to a hydrogen, and they're pretty important too.